Let us see the principle of moving coil galvanometer. This is moving coil galvanometer of suspension type. This is a rectangular coil suspended from a conducting fiber, and this is a soft iron cylindrical core. This is north pole and this is south pole of a U-shaped magnet. This is the front view, and this is a hairspring to provide additional restoring factor, so that the coil can bring back to its initial position after taking readings. This is a torsion head, so you can arrange the orientation of the coil, or you can align by turning this coil as to set up the plane of the coil before reading in the proper way. You can use this screw. This is called torsion head of the suspension coil. And these are two leads connected to binding screws for external connections. We know that when a coil, irrespective of its shape, whether it be rectangular coil, circular coil, or any other coil, it will experience a torque, so that it will deflect in a magnetic field when a current is passed through it. We pass the current to be measured through this coil, so that it experiences a deflection torque, which is now B. Now B cos theta. Here cos theta is made one unity by proper design of the magnetic pole pieces. The pole pieces are curved to form a cylindrical surface, so that theta will always be 0, and deflecting torque will become B, NABI. Now the coil deflects or turns, twisting the suspension fiber. As the coil turns, the suspension fiber will twist. Because of rigidity modulus of elasticity, the suspension fiber will oppose this twist, and a restoring torque will develop inside the suspension fiber. That restoring torque is given by z theta, where c is a constant of the fiber. C depends upon the modulus of rigidity of the material of the fiber, length of the fiber, cross-sectional area of the fiber, and so on. So, C theta, this torque will deflect the coil from its initial position. This will try to bring the coil back to its initial position. When the 2 theta is the angle of rotation of the coil produced by the current. When the two become equal in magnitude, the coil will come to rest in its deflected position, so that we can write now B equals C theta, from which current passing through the coil, which we have to measure, I equals C by nab into theta. Theta is usually measured in millimeter using a special arrangement called Lamban scale arrangement. We will see its details when we deal with optics. Now C is a constant of the fiber, N is the total number of the coil, A is the phase area of the coil. So N into A are constants of the coil. B is the magnetic field strength provided by the magnetic poles, which are permanent magnets, U-shaped permanent magnets. So B is a constant. That means C by NAB is a constant K, then I equals K theta. So by measuring theta and knowing K, we can measure strength of the current I. Well, what is the advantage of these instruments? First thing, it is very sensitive. You can measure very, very small current using this instrument. The main advantage is I is proportional to theta, or deflection is proportional to the current passing through the coil. That means you can provide a linear scale along with the instruments. If one division reads 1 milliampere, then two divisions read 2 milliampere, 5 divisions read 5 milliampere, so on. Such an arrangement is called linear scale. So you can directly measure current strength using a linear scale because deflection of the coil is proportional to current. This is the main advantage of moving coil galvanometer. Now, instead of suspending the wire, you can pivot. Suspending the coil, you can pivot the coil on a pin, and using an additional spring, you can provide the restoring torque. Now, the two factors we have to consider separately. One is called current sensitivity of the galvanometer. This is defined as current sensitivity is deflection per unit current. That is, what is the deflection produced when 1 ampere current is passed through it? That quantity is called current sensitivity, theta by I. Usually it is expressed in millimeter per microampere or milliampere and so on. Theta is in millimeter, I is usually in microampere or milliampere. So current sensitivity is usually expressed in millimeter per microampere or millimeter per milliampere and so on. And theta by I, from this expression, theta by I is NAB by C. So you can increase the sensitivity by increasing the number of turns of the coil, by increasing the area of the coil, by increasing the magnetic field between the magnetic poles. Therefore, this is the reason now we introduce a soft iron cylinder inside the coil. This will increase B value inside the coil. That is the purpose of the soft iron cylinder. It will increase the strength of the magnetic field acting on the coil. And again, by decreasing C. C is called couple per unit twist of the suspension fiber. Couple per unit twist or torsional rigidity of the suspension wire. C is a constant of the fiber. Now, by taking these steps, we can increase the sensitivity, current sensitivity. Increase the number of turns, increase the phase area of the coil, increase the strength of the magnetic field, decrease the couple per unit twist of the suspension fiber. Now there is another factor related with galvanometer that is called voltage sensitivity. voltage sensitivity is defined as deflection per unit voltage applied to the galvanometer. It is expressed in millimeter per microvolt or millivolt, theta by V. Theta by V, but V equals I into R, where R is the resistance of the coil. By Ohm's law, V is IR. So, voltage sensitivity becomes theta by IR. Theta by I is the current sensitivity. In short, voltage sensitivity equals current sensitivity divided by resistance of the coil. Or theta by V equals, we can take it as nab by ZR. So to increase the voltage sensitivity, what are the measures to be taken? 1. Increase number of turns, increase the phase area, increase B, decrease C, decrease R. So these are the factors affecting voltage sensitivity. C. You cannot make or you cannot increase current sensitivity and voltage sensitivity simultaneously. Why? Now, when you increase N, current sensitivity will increase. But as N increases, resistance of the coil will also increase. If we increase number of turns 10 times, then resistance increases much more. When you increase the number of turns, length of the winding wire or length of the wire used for the construction of the coil will increase, and thus its resistance will increase. Moreover, if you want to increase the number of turns, you have to shorten or decrease or reduce thickness of the wire. So, as far as resistance is concerned, when you now increase the number of turns, length of the wire increases. At the same time, thickness of the wire or area of cross section of the wire decreases to make the coil compact. Both these factors, that is increase in length and decrease in area of cross section, increase the resistance much more effectively than increase in number of turns. Increase in number of turns means voltage sensitivity will increase, but increase in when you increase number of turns, resistance increases much more effectively, so that this takes predominant role. As a factor, consequence, theta by V will reduce. So when you increase the current sensitivity, its voltage sensitivity will decrease to some extent. This is the reason why you cannot increase current sensitivity and voltage sensitivity simultaneously. Now, other questions we will come across connected with discussion of moving coil galvanometer. For the time being, thank you.